All right. So when it comes to vegetation management, the reason you want to have a good solution is because the majority of your outages at a utility, an electric utility, is going to be from contact or falling trees. So the majority of our power lines in the U.S. are still above ground overhead lines. We have some areas that have underground lines, but the majority are still above ground, and tree damage is the number one cause of outages. Right now, most utilities, the way they deal with the vegetation management process is a cycle-based trimming. So over time, they've learned, okay, every 4 years, let's revisit these feeders and do the trimming, which doesn't take into account, say, hey, the species of trees or the weather or how fast things grow, right? So the main issue is, how do you determine where you want to trim to prioritize your worst possible locations? Where are the trees closest to your power lines? Where's the vegetation most dense? And that way you can have the companies come in and bid for the specific spans or feeders that you need to focus on. So we initially started this solution with satellite data. What you're seeing on the left side here is spectral analysis. So basically we took 4-band imagery, RGB, NIR, and we're able to calculate some indices. What you're looking at here is NDVI. So basically it's bringing out anything that's vegetation. In this case, it would be trees, grass, bushes, everything, right? And we built out a model that could differentiate trees from grass and then use the client's GIS data itself to calculate encroachment. Within the power line, within 12 feet of the power line, what percentage of it is vegetated, how tall are the trees, etc. The main drawback with this solution is A, it relies on the GIS accuracy that the utility has. And depending on the utility, that may be within a foot or two, or you could be off by 5 meters. So on satellite imagery, you are not going to see power lines at all. It's not, we don't have that kind of resolution, nor can we detect the spans and everything. So between that and our ability to get the height of trees through satellite, we moved on to using Geiger mode LiDAR. Shrini from Sanborn will talk more in detail about Geiger mode LiDAR, but the idea is it's a form of LiDAR that we can fly aerially and collect a massive amount of data at a much faster speed than, say, backpacks, drones, or the traditional linear LiDAR. Here is an example of what you would see from LiDAR data. I'm guessing a lot of people have probably seen some sort of similar visualization. What you're seeing here is a substation. The green are the trees around it. The pinks and yellows are the power lines. So on top of the LiDAR collecting this point cloud of information, it also has a classification. We classify the vegetation, the power lines, the poles, buildings, and ground. So the idea is we now have these massive point clouds that every single point has a Z as well as an X and a Y. So we can plot all of the power lines, the vegetation, and get their relative height and compare them to the relative height of the power lines themselves. What you're seeing here on the left, the yellow is the power lines. It's a top-down view of the LiDAR data. The little pink dots are the poles, and the green is the vegetation, specifically the trees. And we use this information along with a digital terrain model to get the relative height. By default, the raw data has an absolute height of everything, so that's why the digital terrain model is important. Something I mentioned earlier, this is a transmission line, but whenever we first started doing this work, we noticed that 10% of the power lines weren't within 10 feet, and 43% of the power lines were not within 3 feet of the actual location of the power line, based on the GIS assets that they had. The other thing is, usually the GIS asset or the pole might have a height on it, but you can't assume that the entire wire, especially on a transmission line, is going to be at that height. Transmission lines have massive sag, and especially under load. And even distribution lines are going to differ, especially if you have them stacked or sideways. There's so many different configurations. So when the clients expect us to be accurate to within a foot, as in there's a branch within 1 foot of this power line, that's the client GIS assets are already out, right? Because those aren't within 1 foot to begin with. So there are a few challenges in processing this LiDAR data. As you can imagine, it's very good at detecting trees, buildings, and it even captures the wires quite well, but there are certain limitations. So if there's wires made of a particular material, say copper, it might not reflect the LiDAR properly, and you might get a sparser view of that wire. On this picture here, if you look on the left picture, those red dots are all that were captured for this particular span that was running past these trees. The blue dots is what a full, dense power line you would expect it to look like. You'll see there's multiple blue lines here as well because they're stacked vertically. So you actually have 3 different power lines here. So that's one challenge. How do we deal with these sparse wire points? Another challenge, as I mentioned, is you can have any configuration you can think of power lines. 3 horizontal, 3 vertical, 6 stacked vertically or horizontally. And from one span to the next, you might actually swap from horizontal to vertical. And unless you have LiDAR data, you're not going to be able to keep track of that information within the GIS assets. So here's the solution to the sparse LiDAR points. If you look at the blue, that's actually what we had for a particularly tough case here. And what we need to do is automatically determine what type of stacking is here. So given the number of points, do we think that there's 6 lines here? Is it a 3-phase? Is it a single phase? That information might not be available from the GIS asset itself, right? Or the pole data. So once we've detected if it's horizontal, vertical, or hybrid, then we isolate which ones we think belong to each of the, if we say there's 3 wires in vertical, we say, okay, of these dots we've seen based on their X, Y, and Z, which one belongs to line 1, which one belongs to line 2, which one belongs to line 3. And then from there we have a few different methods of, we call it gap filling or vectorization, of drawing catenary curves through these lines. We may have to throw away a few points as we can't quite determine if this belongs to this line or this line, but at the end, we actually fill this and push it back to the LiDAR data. So this is actually adding to the point cloud a density of line, however we determine, maybe once every foot, once every 3 feet, however we want to do that. This is just a quick view of the wire types that you might see in a common residential urban area. The other thing that we had to work on here is when LiDAR collects data, it collects the data of what's there. If there's communication lines, if there's guy wires, transformers, it's going to capture it all, right? And so especially with service wires, which are the wires that are coming to your home from the main line, or the communication lines, most of the utility companies we've worked with have 0 interest in finding out if these are within striking distance of a tree. And most of the time, if you look at a communication line, after this project, I've been looking at every single span and every single feeder that I passed by. Comms lines are covered in trees. It's just, nobody's going to go deal with those. The primary lines that are really what they're concerned with, even the neutral is not generally important to them. So we actually have to go in and see, okay, we have all these lines. Which ones are the primary lines? And one of the biggest issues is the comms lines are usually much thicker than energized lines. So they're going to get definitely picked up. And on a 30-foot pole, the comms line might be sitting at 20 feet. But on a 50-foot pole, the comms line could be sitting higher at 30 feet. So you can't just say, hey, just cut everything off under 30 feet, because then you might start getting rid of energized lines. So we actually have to use a base threshold. Anything under some 20 feet has to be a comms line. That can't be energized, right? But then from there, we have to use some more logic to determine, hey, are we seeing lines 10 feet above us? If we are, then we're definitely not the top primary lines. And there's A, a rule set, and B, some more advanced logic to determine that. The last thing that can happen is when we're talking about these point clouds, there's millions and millions of points, right? And the classification process is very good, but you're still going to end up with misclassification. So one is you can have a chunk of wire points misclassified as a veg. And what that does is basically instantly creates encroachment. If you're seeing veg points right next to wire points, then the distance between them is basically 0, and you're flagging that as the worst possible score. So we need to do additional processing on the LiDAR data to try and find these little clusters of misclassification and ignore them. And so at the end of the day, what do we provide the client? We generally provide the client with one, we take the KPI data, all the data that we gathered using strictly the LiDAR location of the wires, the LiDAR location of the poles and trees, but then it needs to be attributed back to the GIS data. Because I can't just say, okay, your problem's here, right? I have to say, your problem is on this span, on this feeder, so that they know where to go to do the work, right? So we attached back some KPIs to the actual GIS data itself. And this is 2D distance, and you can think of 2D distance as you're looking straight down. You don't care how tall the tree is itself. How far away is it from the power line? And then the 3D distance is the actual distance, like measured distance from the closest power line to the closest veg point on that span itself. And finally, we have something called encroachment volume. So how many points are within 1 foot of the power line, within 3 feet, 5 feet? And usually these distances are decided with the client. Some clients would use 3, 5, 7, and 10. Some other one, they'd say a D is if it's within 1 feet, right? Tell me all the ones that I have encroachment within 1 feet. I'm going to go knock those out first, right? Okay, so that is the quick overview of LiDAR-based vegetation management. Let me stop for questions there. And if anybody has any questions. Sure.
I saw you, and maybe you're going to mention it here. You mentioned SAG. Do you guys factor in blowout as well?
Right now, it's a very simple catenary curve that whenever we're vectorizing, we try to keep that, but we haven't done anything more advanced there. Sure.
What's the source of your LiDAR? Are you procuring for LiDAR? Or?
We are procuring our LiDAR from Sanborn, and that Srini will be presenting later.
How much of that differentiation and classification is AI versus a human behind that?
So again, I think Srini's going to talk about this, but the first pass of the classification is fully automated, and then there's a second manual pass that corrects some, focusing just in the right-of-ways, focusing some of these misclassifications we can see.
You'll probably answer this, but I'll ask you anyway. Are you only collecting during full leaf on, or are you able to do it when there's less leaves or no leaves?
We've done both. So depending on when the client agrees and does, and they want it for this year, we've done leaf off, and then we've worked with Sanborn to do what we call a leaf off correction, because once the leaves are on, so the leaves add distance, but they also add weight. So the branch is going to come down, but it's also going to go horizontally. But leaf off does actually provide you with more detailed LiDAR data of the branches and the trunk structure itself, because the leaves aren't there to absorb the LiDAR. Yeah. So they both have their uses. If it were me, I would like one of each per season, but that's a monetary issue. Any other questions? Okay. So I have 2 topics next. I'm not sure if I'll get through next. One is outage prediction. I know some people are interested. The other is the more recent work we've done with calculating above ground biomass throughout the world. And this is for the use of carbon credits and things like that. So any show of hands or anybody can yell out and I'll pick one and we can go over that. Okay, that's what I thought would happen. So let me skip ahead. Here we go. So we started this work maybe 2 years ago now. And the idea is, so carbon sequestration and actual carbon credits are a huge growing topic nowadays. And we all know that trees are very good at converting carbon dioxide to biomass, right? So the idea of this is, can we predict the available carbon in an area, say in the middle of the rainforests in Brazil or Mozambique or Argentina, wherever it is, because there's two sides of this. There's the companies that are going out and analyzing all of these forests and saying, this is how much above ground carbon we have here, and we want to sell these credits. And then and then there's the middle ground. There's companies that are validating this information so that, hey, yeah, this is reasonable. You didn't just make this up, or we've seen this before. You don't actually own that land, so you can't be selling it, right? And then on the other side, there's the companies that want to buy the credits from these areas. So the idea is they pay them to maintain the land instead of cut it down for lumber or whatever it is. And it's creating jobs as well as preventing that carbon from being lost. So the manual approach to getting how much carbon there is, I think someone talked about it during the panel earlier, is you actually go out to the field and you do measurements. You can take a few trees per species, and actually the real way of finding out how much carbon is in something is to burn it, right? So that's what they do. They take the tree and they burn it and they say, hey, this is how much carbon was in there. And then there's things called allometric equations where you can calculate how much carbon you should expect in a particular species of trees. And this is usually done using their height and their diameter at breast height. So however the diameter would be at about here. Not mine. For some reason, it's not my breast height. It's much taller than me. And then we can use this to extrapolate to other trees in the field, especially if you have, say, a tree farm that they're building new trees and they're all eucalyptus. That's a common one to plant, right? So now you can take that area and know, okay, it's eucalyptus. If you can calculate the height of these trees, then you can estimate for eucalyptus how much biomass should be here. So, like I said, currently the best way of doing it accurately is manual assessment, but that doesn't scale if you want to go through the entire rainforests of Brazil, right? So the idea here was to combine multiple data sources to calculate AGBD. So the first data source is Harmonized Landsat Sentinel. So this is a pretty common data source. There's a few different versions of it. It's about 30 centimeter resolution, has quite a few different bands. It's not just RGB, NIR, but there's, I think, maybe 14 bands in the base product at different spectral ranges, and different ones can detect different things in the atmosphere or in the ground or in the trees. So that is the data we're using as our input data set for training models. The other, so this is the visible spectrum, but we also have a much bigger range of data that is collected through the Harmonized Landsat. The other piece of data is LiDAR data, but not in the way that I had presented previously, which would be like drone or aerial LiDAR. This is actually LiDAR data coming from a LiDAR piece of equipment that was attached to the ISS, and it actually captures it from that level, and will give you the height for that pixel. So it will give you, say, the 95th percentile height, the average height, a range of heights, and it will also have an AGBD, which is AGB density per pixel, right? And this is based off of equations that NASA worked with forestry experts and universities to determine, given this height, what should we expect the AGB to be in this pixel. So what you're seeing here is basically the JEDI LiDAR passes across in swaths, and that's what these red lines you're seeing is. So it does not cover the whole world in any way, shape, or form. It's very sparse, but it is consistently following this path, and that is what we would treat as our label data, right? Because this is our height and AGB. Can we use HLS data that has this full spectrum of data to be able to calculate A, can it be height, or B, AGB directly? So one of the biggest issues is cloud cover, especially when we're talking about tropical areas. So the input image, JEDI doesn't have to worry about cloud cover because it's LiDAR data, but HLS satellite imagery definitely has to worry about cloud cover. And usually there's one snapshot every 6 or 7 days, I believe it was. And what we do is we go through each of these HLS imageries, HLS tiles, and they come with a bunch of metadata. And one includes a cloud mask, a water mask, all of these. And for each TIFF image, we would actually overlay them and only keep the pixels that don't have cloud shadows, and a few other things are filtered out there. And we basically build a composite image across a date range. And that date range is very dependent on where in the world you are, because you're trying to capture, in this case, you definitely want leaf-on seasons, right? You can't do this with leaf-off. So Southern Hemisphere, you have to flip the months. Certain places near the equator, you need to pick months that don't have that much cloud cover, right? Or else you end up like tiles, like T4 here. That tile is completely covered in clouds. You've got no data, that snapshot, right? So usually we span something from 3 to 6 months of data in a given year for us to build one cloud-free image. Now, on the other side is JEDI. As I mentioned, JEDI data is very sparse, right? We don't have labels everywhere because there's just one piece of equipment. And on top of that, I think twice now, they've taken it off the ISS and turned it off for like 9 months to a year and then put it back on. So there's gaps of data missing. So we have a filter on all the JEDI data as well, based on, we want to focus on night observations more than day observations. And there's a bunch of metrics built into the JEDI data that we use to filter which pieces of data we want to keep. So here's the data flow in general. We run the HLS cloud removal. So we take however many 3 to 6 months of data and create this says monthly, that's old, image for 1 year. So basically we're treating it as 1 year at a time. Then we get the AGB data, like I mentioned, that goes in those tracks and filter it to what we want. And the next step is we need to combine those data sets. And the important part here is that they're completely different resolutions, right? So they need to be harmonized so that they're both on the same pixels, right? So you don't want these 30-kilometer HLS tiles, and then you have JEDI. The JEDI pixel overlaps 6 tiles. So we basically go through a process that we call harmonization to combine these 2 pieces of data so that they're on the same grid, basically, right? Same resolution, same grid. We split this data into a train and test set, and then we generate a model. We tried a few different models. We started with a random forest pixel-based model, and then we eventually settled on a UNet model. This is a convolutional neural network model that is built for image segmentation, right? So this model is built for image segmentation, and we're trying to use it on satellite data, which is, again, an image at the end of the day, right? So how do we measure performance? We don't go out to each of these areas and cut down trees and burn them, because that would not scale. So we have the basic accuracy metrics you would see in any ML solution, RMSE, some correlations, and we actually break them down into bins. So what you're seeing here is the actual AGB, above ground biomass. That's in tons per hectare is the unit. And depending on the bins, the accuracy is quite different. For example, anywhere from 50 to 200 is our best accuracy. Once you go above 250, 300, the issue is there's not that many places in the world that have that dense of biomass, so you don't have many samples. And the 0 to 50 is also a little bit harder to predict, as now you come into the noisy issue of brush and things that could be biomass, and it's hard to tell if you got the height quite right at the lower end of the height. So outside of these, one of the most important parts of actually validating these results is visual inspection of the data, because we've seen many pieces of data where the accuracy metrics are the same, but when you go and look, the localized data is bad and the generalized data is good. So if you go focus on a plantation, it might not be very accurate. For the whole tile, the accuracy is decent, right? And so those metrics don't tell you the whole picture. The other thing is you could have some anomalies in the data only in certain portions that you're not going to capture by looking at the actual RMSC and other metrics at a tile or multi-tile level. And like I mentioned, we have an over-prediction on the low range, 0 to 50, and an under-prediction of high AGB, anything above 300. And another reason for this is because the HLS data actually gets saturated. After a certain point, the band values, that even if they're bigger, it doesn't actually give us any more information, right? So like I mentioned, there's sparse ground truth data for validation other than JEDI. So at first, we did this for countries at a time. We started with Brazil and Portugal because we had more species data there as well. But at the end of it, we basically picked all of the biomes in the world, picked one year, and generated an AGB map for the whole world. When I say the whole world, you see at the top of this, it's clipped most of Canada and the tops of the world. That's because JEDI does not go above and below certain latitudes, and they don't collect. There's just no data to collect there, right? So we have to stay within these. Luckily, that includes most, if not all, of the actual places that are of need for this, as far as tropical biomes and areas with large vegetation, plantations, places where you would grow any sort of types of plantations. And you'll see the Brazil with the rainforest definitely has some of the highest AGBs in the world. And then in the center of Africa, Congo, DRC, and then a lot in the Indonesia, South Pacific region. As you may imagine, the tropical areas with all the forests. So this is just a comparison of our model that we had back in 2023 in a particular location that they were trying to assess they had grown, I want to say eucalyptus here, and they wanted to assess how it was doing, if it was growing. So we could actually do this for 2021, 2022, 23, and 24, so that we can show the change over time for some of these plantations. From the client perspective, one use case would be they would come in with a polygon and say, hey, in this, what is the current biomass? What was it 4 years ago? And if we tell you whether we're going to plant a specific species there, can you tell us what the AGB will be in 10 years? So the other piece of work I don't have here that we're working on is the growth metrics. So you would take we have a growth model where we would take the species, the year it was planted, and plan out the next 30 years of this is what you should expect from your AGB growth, and this is when it'll even out and the trees will mature. Any questions?